earlier lectures, we mentioned that for multiparticle systems, the change in translational kinetic energy can be thought of as distinct from internal energy changes, changes of energy inside the system, such as change in rotational energy, a change in vibrational energy, both vibrational kinetic and potential energies, the change in thermal energy, or change in chemical energy, and so forth. Today we'll discuss how this distinction can be used to solve some challenging problems with the energy principle. The main idea is that we'll apply the energy principle in two distinct ways to the same situation. First, by applying the principle to a simplified view of the situation that focuses only on the change in translational kinetic energy. And then we'll apply the energy principle to the full multiparticle situation to solve for unknowns associated with the internal energy changes in the situation. Let's introduce this procedure in the context of an example. Imagine a disk of mass m that can slide on smooth ice with essentially no friction. Initially, the disk is at rest with a string of negligible mass wrapped around the rim. The string is pulled tangentially with a constant force F as shown. At the instant when a length L of the string has unwound from the disk, the center of mass of the disk has moved a distance d. What is the rotational kinetic energy of the disk at that instant? As usual, we start with a fundamental principle, the energy principle, and we choose the disk as our system. The energy changes that we would expect in this multiparticle system are delta K trans, the translational kinetic energy, and an internal energy change in the form of delta K rotational for the change in rotational kinetic energy about the center of mass. We say that the rotational energy is inherently an internal energy of the multiparticle system because we could imagine a related situation where, instead of the disk, we truly have just a single point particle with exactly the same mass placed right where the center of mass of the disk is. Then we imagine that the same forces from the surroundings act on that point particle as it undergoes the same change in position, the same displacement. Then in this case, we would have only one energy change, the change in translational kinetic energy, because a point particle has no internal structure and therefore has no internal energy changes. This simplified problem, with only translational kinetic energy changes, is, in fact, a simplified picture of the original problem that we call the point particle model. The textbook calls it the point particle system. It's a very helpful picture because we can solve for the change in translational kinetic energy in this picture, and it will be the same change in delta K translation as in the original problem. So let's do that. The only non-zero work done is that done by the pulling force F, which in the point particle model acts through the displacement of the point particle. This is the only displacement in this model. So we have the change in translational kinetic energy is the product of the magnitude of F times d, the magnitude of the displacement of the point particle. Now we can return to the original multiparticle situation, which the textbook calls the real system. Now let's apply the energy principle to this. The change in system energy in the full problem has two parts. As we said earlier, delta K translation and delta K rotation. Now, however, we know delta K translation from solving the point particle model earlier. We only need to find the energy transfer in the full problem. The only non-zero transfer is the work done by the force F. Now, here's where we need to be careful. When we compute the work for each force in the full problem, the multiparticle situation, the displacement that we use is the displacement through which the force actually acts. That is, the displacement at the point of application of the force. Let's look carefully at the displacement associated with the force F. We see that the magnitude of this displacement is d plus L, because both the center of mass moves a distance d, and at the same time the string unwraps by a length L, so that the work done by the force F in the full problem is the magnitude of F times d plus L. Substituting this in and solving for the change in rotational kinetic energy, we find that this is equal to the magnitude of F times the length of the unwound string L. Since K rotation initial is 0, the disk was at rest, then this is also equal to the final rotational kinetic energy, which is what we were trying to find. So just to recap, we have discussed a procedure using the energy principle for finding quantities associated with internal energy changes in multiparticle problems. The procedure applies the energy principle to the same setting, but in two distinct ways. First, the energy principle is applied to a simplified point particle version or model of the original problem, with the goal of discovering quantities associated with the translational kinetic energy. Here it is important to keep in mind that all non-zero work computed in this simplified problem must use the same displacement, the displacement of the point particle, which is the same as the displacement of the center of mass of the original system. Then, the energy principle is applied to the full multiparticle situation where we make sure to compute the work using the correct displacement for each force, the displacement at the point of application of each force in the full multiparticle problem. We can then solve for quantities associated with the internal energies of the full multiparticle system with help from results we obtained in solving the earlier point particle model. This procedure is very powerful, and we will use it to solve some very challenging problems. We'll begin to practice that in examples coming up in the next few lectures.